Good morning to all. I am Gauri PS, lecturer, Department of Radiology, Global College of Allied Sciences. Today we are going to discuss about gamma camera. First introduction. The gamma camera was designed by Halo Anker of Dona Laboratory in Berkeley, California in 1950. He uses technetium 99M gamma rays and characteristic X-rays to form the images. The technetium 99M is injected intravenously into the body, and it will be concentrated in the organ of interest, and it will be emitting the gamma rays which will be detected by the gamma camera. It is a planar imaging which produces the images of the radionuclide distribution in the patients. The next topic is equipment. The equipment, that is the gamma camera, consists of collimator, scintillation crystal, photomultiplier, position and summing circuit, pulse height analyzer, computer and display system. First we are going to look about collimator. The collimator controls the field of view. Usually the collimator is located between the crystal and the patient. It will be allowing the X-rays or the gamma rays which were originating from a certain directions in the crystal. The commonly used collimator consists of multi-hole collimator or parallel hole collimator. These holes in the collimator will be accepting the gamma rays which were arising from the perpendicular direction to the crystal. If the rays do not come from a perpendicular direction, it will be automatically absorbed by the collimator walls. Next we are going to look about scintillation crystal. The scintillation crystal is a single large circular crystal of 500 mm diameter, 9 to 12 mm of thickness. It will be absorbing 90% of the technetium 99M gamma rays by the photoelectric process, whereas 30% is done by iodine 131. Usually this scintillation crystal is kept within an aluminum cylinder with one of its side as transparent. It is used for the entry of the gamma rays. When a gamma rays enter into a crystal, it produces a flash of light and UV rays. It is commonly called as light photons, which will be undergoing a multiple reflection with a time of less than a millisecond, and they will be reached to the photomultiplier tube. The other side of the scintillation crystal is usually coated with a titanium compound. The amount of light which leaving the crystal will be depending upon the collimator holes. A flat lucite coupling is usually provided between the crystal and the photomultiplier tube to avoid the loss of light from the crystal. Next topic is photomultiplier tube. Usually the scintillation crystal is coupled together a number of photomultiplier tubes. Each photomultiplier tube is an evacuated glass envelope having photocathode. Evacuated glass envelope, that means it is without an air. It absorbs the light from the scintillation crystal and it will be emitting the photoelectrons. These electrons, when they pass through the series of diodes which are connected together, they will be producing an additional electrons. These electrons will be all accelerated towards the anode side and they will be creating a charge pulse. Each photomultiplier tube will be connected with a preamplifier where the signals will be amplified further to the next level, that is to the next, they will be going to the position and summing circuit system. The next topic is position and summing circuit. The pulses from the preamplifier are fed, that is passed to the position and summing circuit. In the position circuit, they will be receiving the pulses from the individual preamplifiers and they will be producing X position pulse and Y position pulse. This X and Y position pulse will be together joined and they will show the position, that where the interaction will be taking place within the crystal. Usually the summing circuit consists of the pulses from the individual preamplifier which is added together and they will be producing an Z pulse. These Z pulses is then fed, that is passed to the pulse height analyzer system where they will be done for the energy analysis. The next topic is pulse height analyzer. The photo peak, that is plus or minus 10%, will be set as a window level in the pulse height analyzer. This pulse height analyzer will be producing the logic pulse only if these pulses are kept within the preset values. These selected pulses will be called as counts. If there are pulses which are above or below the presetted values, they will be rejected back. If there are more, there will be more pulse height analyzers if more energy is produced. Next is computer and display. The pulses are digitized by the analog digital converter. The X, Y pulses and the logic pulses of Z are then passed to the computer. It will be recording the Z pulses as counts in their memory location with corresponding to their X and Y coordination. When a large number of pulses are produced, there will be a large number of counts produced in the memory location. Then they all will be stored together as a digital image. This image will be then displayed on a monitor screen where there will be further production of the images are taken place by the computer software.